Hey guys, BuildZoid here, and today we're going to be taking a look at the datasheet of the NCP81274. So this is the voltage controller on the GTX 1080 Ti Gamerock I have, so that the palette card. And also I think it's also used on the FTW3 from EVGA. And so today we're going to take a look at some basic modifications for like voltage control, switching frequency, and V-droop, because we want to, ideally I'd want control over it, but we can also just turn it off. And turning it off is better than having V-droop, because on LN2, there's a problem with the voltage. Generally what happens is like you have these situations where like the silicon stop, like the GPUs stop working if you give them too much voltage. And then if you just have like then when you're under load and the voltage is dropping down, it's just like you can't clock as high because the voltage is way too low. So anyway, we're going to take a look through this and set up all of those modifications. So let's get right into it. And the easiest way to probably, so the first mod is, of course, just basic voltage control. And that's really, really easy to do because this chip uses a PWM vid interface, which is part of the NVIDIA Open Voltage Regulator 4 Plus specification. And the PWM vid interface is great because you basically have, let's see, zoom in a bit, move over, basically have these 4 pins right here. So you have like VREF, REFIN, VIDBUFF, and PWM vid. So PWM vid is where the PWM vid actually comes in. So that's a PWM signal that comes from the GPU and into the NCP81274. That then gets, I think, filtered on chip and then output through the VIDBUFF pin. That VIDBUFF pin is connected through a circuit to the ref in pin and also the VREF pin. VREF literally is just a 2 volts output. So that's just 2 volts. Ref in is the setting for the output voltage of the VRM. So whatever voltage you have on on ref in is the output voltage of the VRM before V-droop. So if we have, say, say we have 50 millivolts per 100 amps of V-droop, and we have ref in set to 1.2 volts, and we have 200 amps coming out of the VRM, we're going to get 1.1 volts at the GPU core. If we have 100 amps coming out, we're going to get 1.15 volts, and that's all with ref in at 1.2 volts. So that's also why we're going to be taking care of the V-droop thing so that we get manual control over that, because V-droop obviously exists to like compensate for the fact that VRMs can't respond to load changes instantly. So you get a bit of like you always get a dip in voltage right as you start a load, and you also get a spike, and you get a spike in voltage as you come out of load. But the thing is just like it's for the purposes of extreme overclocking, it's just like too much V-droop is definitely worse than not having any V-droop at all. Ideally, like in a perfect world, you'd want to like perfectly, set a correct level of V-droop where it's just right. But given the choice of on or off, off tends to be better than on for V-droop. So that's kind of that, but we'll deal with that later. For ref in, basically what you're going to do is you need to disconnect the VIDBUFF from the ref in pin, and then you can just put up a voltage divider between VREF, ref in, and ground. So that's all very nice and simple, right? So you just use a potentiometer for that with VREF, and I normally use I use a 1 kilo ohm potentiometer with a 330 ohm resistor between VREF and that potentiometer. So and then a 680 ohm resistor to ground. And the end result is that I basically get a minimum voltage setting of like 600, roughly around 680 millivolts, and a maximum voltage setting of around 1.68, which is significantly higher than what you would need on liquid nitrogen. Like on liquid nitrogen, a 1080 Ti will, under good conditions, scale up to about 1.55 volts. Some cases they'll scale all the way to 1.6, but most of the time you're going to be looking at about 1.55, like 1.5 to 1.55 range, or even 1.45 if something's really wrong, or the card just is weird and doesn't like voltage. So that's that. And if you actually want to see what the circuitry for that looks like a bit better on how it's hooked up, so there you can see how the vid buff is connected to the ref in and the vref. And you're just gonna, like, honestly, on the card, you would just remove this resistor right here, which, let me just quickly do that. So you would just remove that resistor, and then, you know, after that you can run your potentiometer. And I use a 1 kilo ohm potentiometer because obviously the VREF and the ref in pin, after you've lifted off this resistor right here, these still have, like, I think on my card it was like 22 kilo ohms of resistance between each other. So I mean, you could choose like an appropriately sized potentiometer, but it's just, for personally, I find it's more convenient to just use a potentiometer so small that whatever was there originally is just completely ignored at that point. And then I do the, and whoops, and this is what I get for trying to draw with the mouse. So yeah, and then you get the first resistor, which is the 330. Then you get the potentiometer, which is 1K, and then you get the third resistor, which is 680, and then that goes off to ground. Lovely. So, yeah, that's basically all you do, and you get full manual voltage control with that. So that's how I like to do voltage control. The nice thing is that since this is not actually part of the voltage regulation loop, like this is not part of the feedback loop whatsoever, you're not at risk of like screwing with the feedback loop, basically, because you're not actually messing with it. This is literally how the voltage is set on one of these chips. So this is like this is equivalent to like on a fully digital chip, if compared to like a fully digital chip, this is literally like, you know, telling it to output 1.2 volts. If you set ref in to 1.2 volts, it's like telling it to output 1.2 volts. It's not the same thing as with a feedback pin mod, where you're basically tricking the chip into outputting a higher voltage by messing with the voltages it sees on the output of the VRM. So it's a nicer way of doing the modification in that sense. Anyway, let's move on to the switching frequency, because switching frequency is super easy to do. We're just going to do that the easy way. We're just going to search for that in the data sheet. There's no, I mean, we're going to see it right here. So pin 27, FSW, resistor to ground from this pin, sets the operating frequency of the regulator. So we're just going to copy paste frequency in here, and then we're just going to search through the data sheet until I get what I want. So frequency, nope. Nope. There we go. Switching frequency, a programmable, blah-de-blah-de-blah, blah, 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 blah. Table 19 lists the switching frequencies. Yes, I have read this data sheet before. So table 19 lists the switching frequencies that can be set using a discrete resistor, using discrete resistor values for each phase configuration. So if we scroll all the way back up to the top, which we're going to get to table 19 soon. So 8-phase voltage controller, the switching frequency goes from 250 kilohertz up to 1.2 megahertz in 8-phase mode. At lower phase counts, the switching frequency range actually is different, which is kind of neat. And on the 1080 Ti I'm working on, it's actually a 6-phase mode. It's in 6-phase mode because that's a 12-phase VRM using this chip right here. Let's get to the top. This chip right here for the doubling of the PW of the phases. So it's kind of that. And this is this right here is the power stages it uses, and this is a 50 amp power stage. So, you know, very, very, not the most ridiculous 12 phase ever, but a nice enough 12 phase nonetheless. So plenty powerful for my uses, and, you know, nice enough PCB. And of course, the downside to cranking up the switching frequency is that our efficiency is going to get worse. As you can clearly see here, you know, if we were pushing 45 amps on each phase at 500 kilohertz, it would produce almost 8 watts of heat. At 750 kilohertz, we're looking at more like 9. And at 1 megahertz switching frequency, we're looking at over 10 watts of heat output. So yeah, it definitely, you know, harms the VRM's efficiency quite significantly. But the reason why you want to crank up the switching frequency is you get less output ripple, and you also get you get better transient response. So basically, that overshoot I was talking about, with which VDroop exists to compensate for, that the drop and the overshoot you get when a VRM goes from like very low current pull to very high current pull, and then from high current pull to low current output. The instability, like the spikes in voltage that you get from that happening, you can actually, the VRM can quicker respond to changes in current draw if you crank up the switching frequency. So this helps with this does help with overclocking, and there's actually some voltage regulators out there used on some motherboards which will actively crank up their switching frequency as the current draw increases, specifically to basically help them with transient loading. So as well as to lower the ripple at higher current draws while saving power at lower current draws. So yeah, basically being able to control this is, in theory, it should give us more overclocking range. On the Founders Edition, going from the stock's 300 kilohertz to the 600 kilohertz did actually did help a lot on LN2 with overclocking, and you can actually see that in my 1080 in the 1080 Ti LN2 live stream I did. And with this card, though, I'm not sure how much of a difference we'll see, because this is obviously a 12 phase with 300 kilohertz per phase, 600 kilohertz at the voltage controller, which I've checked. Like, I know that because I checked the card running with while it was running with an oscilloscope. So the switching so I'm not sure how much impact we'll have, because we already have more phases, and effectively, like, we kind of already have a much higher switching frequency than what you would have seen on the reference card. But it's like the only downside is that the VRM is going to run hotter, and I don't really care about that. So we're going to see if, cranking up that switching frequency can't give us some nice gains in overclocking range. We could be talking like on air cooling or on ambient. It was already like 10 megahertz, and I think on LN2 it was like plus. I want to say it was like almost 50 megahertz difference. Like it was a pretty big difference from cranking up the switching frequency. So here, with a voltage controller that goes up to over 1.2 megahertz for the lower phase counts, yeah, I'm excited to see what happens, though. You have to be a bit careful, because obviously, as you keep cranking up the switching frequency, you have to keep in mind that not everything you're pushing that switching frequency into will necessarily support it. So like these are meant to work up to like 1.5 megahertz. There are definitely, MOSFETs out there that if you try to run them at like a megahertz, they just won't work, because they take so long to turn on and off that it'll just end up being horrifically inefficient if you keep raising the switching frequency. And in fact, if you keep raising, like if you just kept raising it forever, at some point you would get to a switching frequency where the MOSFET never actually manages to turn on before the PWM signal goes low again. So then you'd just be completely screwed. Like the VRM would just stop working. So that is worth keeping in mind. And then also some doublers will not have, like, doublers themselves will have a limit for how much switching frequency they will support. And unfortunately, here we don't actually have there's no specification of where that is for these. So I'm not sure if these actually have a limit, but I'm just gonna go with I'm just gonna carefully, raise the switching frequency, which that doesn't really mean anything, because it goes up in steps. So it's not like I can slowly tune it up, and it's like if it goes wrong, then it's probably just gonna go wrong all at the same time. But I'm not just gonna max out the switching frequency instantly on the voltage controller. Just to make sure that I don't burn out break the VRM before I get any good scores done. So that's kind of that. And honestly, I think just because I know that say the IR3599 maxes out at 1.6 megahertz input frequency and then 800 kilohertz output. Well, it's actually 800 kilohertz output, and then it's like a quadrupler, so you can actually run a lot of switching frequency into it. But it won't output more than 800 kilohertz per PWM output. So anyway, but for these, yeah, I'm not sure if there's an actual limit, but because of the fact that the 3599 ends at 800 kilohertz, I'll just go these will probably support up to 800 kilohertz output, right? That's a good way to get. It's as good a reason to stop raising the frequency as any other. So anyway, let's go to table 19 now. Table 19. You're not table. There is table 19, and yeah, here we have our switching frequency settings. So we're running in 6-phase mode. I do believe there's a card with this voltage controller in 5-phase mode, or maybe even a couple of cards with it in 5-phase mode. But as you can clearly see here, in 6-phase mode, the stock configuration for the card is like 600, is this range right here. So we're looking at about 41.2 kilo ohms from FSW to ground. So that's the pin 27 to ground. And this is a really easy modification to do, because you just go through this table right here, check what frequency it correlates to, and that's it. Like, the unfortunate thing with this voltage controller compared to, say, the UP9511 is the UP9511's switching frequency goes up as you lower the resistance. So it's actually much easier to modify because you don't need to desolder anything. But with this one, you have to desolder the original resistor, because obviously, like, if you want to go from 41.2 kilo ohms to, say, 60, you need to put, you can't put the resistor in parallel. It does not work like that. So, you basically have to desolder it and then put in a new one. And I do think that these, I'm not sure, I'm pretty sure these are fixed value, so you can't just use like a potentiometer to slide up and down the frequency. And also they do mention like 1% resistor tolerance, so yeah, you can't just like, you definitely don't want to have this hooked up to a potentiometer, just because these have to these should have to be specific values. But anyway, for the switching frequencies that I want, basically I'm gonna stop around there, right? Like, I don't want to go really past that, and that's really not that far off of where it maxes out, which is like 1700s. So for the 6-phase mode, for 8-phase mode, you'd top out at sort of 1300s, or 1.2 megahertz right there. But yeah, I'd basically stop right around that 157.7 kilo ohms resistance, which translates to just about 1500 1500 kilohertz switching frequency. So that would put us on the, if we go back down to that efficiency curve, that would put us on the 750 kilohertz efficiency curve if we're pushing 1.5 megahertz into the doublers. And also, if the doubler decides to do current balancing, because these are one of those, like, these do current balancing, but they do it by basically, you can see how, like, it dumps 2 of the PWM signals onto one phase if one phase pulls significantly more current than the other, to get them to try get them aligned again. And as they show in the data sheet here, you can actually see how it doesn't really work out that well. It just basically was like, instead of having phase A being pushing way more current than phase B, now phase B is pushing more current than phase A. But yeah, that, like, you can at least, like, it does at least have the ability to current balance, but it would effectively, like, your PWM signal right here would effectively be 1.5 megahertz, right? Because if this original one is 1.5 megahertz, then right when it decides to push both pulses to one phase, that would basically turn that into 1.5 megahertz for a little bit. So yeah, that's another reason why I really want to stop there, because these aren't really meant to, like, these are up to 1.5 megahertz. So I'd want to stop around sort of this range, maybe even just be a little bit safer with like the 1339 kilohertz, 1438 kilohertz right there. So 136.6, 157.7, just to make sure that everything, stays within spec. Because I don't really want to, like, I'm not really interested in finding out what happens when you go out of spec for switching frequency on a power stage on a 1080 Ti. If this wasn't a 1080 Ti, I wouldn't really care, but as it is a 1080 Ti, I'd like the VRM to keep working for as long as possible. So that's kind of that, but that's basically the switching frequencies I would stop at. And again, it's super easy to work with, because it's just a resistor. Like, it is literally, you know, as you can see, FSW pin 27, follow that line, resistor, ground, right? So at worst, like, honestly, you just need to remove one of them, and then you can change the resistance. And I'm not even sure what is, like, going on with that. Like, honestly, this is weird. Like, this is odd that they have two of them. Not sure why they've bought, like, why that's a thing here. Is that okay? So that's 26.1K, and that's 125. Oh, I think it's to get like a specific value then. Is it? No, because that's art. What? Yeah. Okay. So datasheet is screwed up right there. So that doesn't make it any easier. So this could just be some kind of formatting error or whatever. I'm not sure. But because if you look at like the UP9511 datasheet, they literally just have one resistor. There's no, like, I can't see a logical reason to have two unless it's for like getting a specific value, but you should be able to just buy whatever value you need if you're buying a resistor for this. So anyway, that's the switching frequency. Now let's go take care of the droop. So let's go droop. No, droop. Why can't I type? There, droop. Nope. There, nope. Well, actually, no, we are at the right place. Programming droop. There. That's the section I wanted to go to. So the signals, CS comp and CS ref, blah de blah. Basically, what we care about is this equation right there, right? And if we look at this equation and this lovely diagram here, we can clearly see that RCS1, RTH, RCS2 are these guys right here, right? So that's RCS2, RCS1, RTH. And then RPH are the resistances from the phases there. DCR is direct current resistance of the inductors. And then that's equal to droop. And so this is really, really easy because basically we just, like, if we want to completely disable the droop, we just need to make this side of the equation equal to 0. Which is rather easy because if you just short over, like, if we make this top half equal to 0, which is really easy because, you know, RCS2, RCS1, if we just short across those, that will make that part 0, right? Because these two guys are, like, RTH and RCS1 are in parallel. So if we just put a like, if we just run a wire across that, this is gone. No more droop. Instantly removes droop. But if these are, and depending on actually what they're set to on the card at stock, which I've already measured these, and on my card they seem to be about around 20, like the resistance from CS comp to CS sum pins is, it's like 24 kilo ohms. So we can actually control the resistance, like we can set the droop up and down with smaller values. We don't need to completely turn it off if we don't want to. Like, I'd assume that if you set it to 12 kilo ohms, because stock is 24 kilo ohms, right? And that's literally this part of that. If we cut that top half, if we cut this top part of that equation in half, we should get half as much droop. So if this is 24 kilo ohms stock, then if we drop it to like 12 kilo ohms, we should get half as much droop. If we drop it to 6 kilo ohms, we should get 25% of the droop. And if we drop it to 0, then we should get no droop at all. So that's how we can mess with the droop settings. So that's nice and convenient. And yeah, so that's nice and simple right there. And OCP, do I care? It didn't, like, the thing is, OCP is actually present, like, the UP9511 has an OCP, but it never tripped, so I'm not sure that I need to worry about it with this thing here, either. So that's honestly, yeah, I'm just not going to bother with that. And anyway, at this point, we've pretty much covered everything I wanted to cover, you know. So for droop, it's just a matter of modifying, and let's actually just take a look at where those pins are. So that's CS comp, CS sum, and if we go back to the programming droop section, droop, right, then we can see that CS sum, CS comp. So if we go back to the top, that's just the pins 22 and 23, so tweaking the resistance between these two pins changes the droop settings. Tweaking the voltage at ref in changes the output voltage. Changing the resistance from pin 27 to ground changes the switching frequency. There. That's all you really need to know about the NCP81274 to get like full manual control of the thing. Oh, and you might also, if you wanted to, you could also mess with the power saving interface. So the PSI right there. And that is, there should be a dedicated pin for that. So that's pin 37. If we look that up, power saving. So that, on this one, it's a bit fiddlier than what I'm used to. Power maximize under various loading, 6 distinct. Yeah, so this is the thing. The device supports up to 6 distinct operation modes called power zones. See table 7. At power up, the controller reads the PSI pin logic state and sources 10. Okay, configuration can be changed by user writing to the... So yeah, this is one of those things you can configure over the I2C interface if you were so inclined. After enable is set high, ignores any change in PSI pin logic state until the output voltage reaches the nominal regulated voltage. When PSI equals high, the controller... Yeah, so this is the part we really care about. When PSI equals high, the controller operates with all phases enabled regardless of load current. So this is what we want to put on the PSI pin. And the reason why we want to do that is, well, all of the phases running all of the time gives us the best voltage regulation. It just also completely destroys the idle power efficiency, because if you're pushing very little current per phase, you're going to end up burning a whole lot of power on just turning those transistors on and off. And not actually, like, and that's really inefficient. Because basically, if you look at the data sheet here, and scroll down, you can see how this like levels off basically towards the end here. So like, yeah, well, and you can, well, this is actually a better illustration of my point, right? You can see how basically as the current approaches 0, the efficiency starts to fall off a cliff. So if you have 12 phases and each phase, and you know, you're pushing 10 amps into the GPU core at idle, and you have 12 phases, you're pushing less than an amp. And so your efficiency is going to be somewhere way down here, you know, or maybe down here if you just kept following that line to wherever it goes. So yeah, it's bad for your idle power efficiency, but since you're not really using that much power at idle anyway, it's like, why would you care? Why? It doesn't matter that much, right? Plus, I honestly, like, for me, this is a benching card, so I do not care. And so you can see that PSI equals high, so we need to figure out when PSI is equal to high. And there's actually going to be that specified in an earlier table, if I remember correctly. Yeah, there we go. So PSI high threshold, minimum voltage is 1.45 volts. I don't know why that sounded so weird to me right now, saying that. It's just like... So, yeah, so that's PSI, and we just need to make sure that it's above 1.45 volts. So the easy way to deal with that would be to just grab like a... Well, it depends on how it's wired up. So let's take a look at that typical application diagram one more time and check out the PSI pin. So PSI, because the thing is, PSI should go off to like the GPU. So we might have a problem, like it might be a good idea to try like disconnect that from the GPU's input. Well, from the GPU's output before we try do anything to it. But unfortunately, that's not like continued on. And I do believe there was something about the... Go to the PSI pin. Yeah, power saving interface control pin. This pin can be set low, high, or left floating. Use a current limiting resistor of 100K when driving the pin with 5 volts logic. I guess we don't need 100K if I just shove 3.3 volts into it, do we? I hope we don't. It says for 5 volts. I'm gonna guess it's just for 5 volts. So Yeah, I'm just gonna use like a 22 or like a 10K and 3.3 volts and shove that into it and hope for the best. If that doesn't work, then we're gonna have to like disconnect it somehow, and that's gonna be the end of power savings on this GPU. So yeah, that's it for the NCP81274. Rather easy to control, especially like everything up until like the PSI pin is relatively simple. Switching frequency is just some resistor values. Ref in is the usual NVIDIA ref in. What else was there? Droop is actually on this thing. It seems to be more controllable than it was on my reference 1080 Ti. That thing was a nightmare because the resistance, like, I did get rid of it, but like the resistors that were setting it were like super low resistances. They weren't anywhere near like a kilo ohm range. So it was just like, oh, so I can turn it on or I can turn it off, which was rather annoying. And because I really did want like finer control over it than just on off, but between on and off, as I said, it's best to just have it off. So for at least for extreme overclocking purposes. So yeah, that's it for the NCP81274 data sheet. For now at least, unless I run into issues with like overcurrent protection, which I don't think I will, just because like normally that should be taken care of by the current monitoring that NVIDIA uses separate from like NVIDIA has through the shunt resistors, and I've already disabled that power limit, so I don't see why the NCP81274 would have a particularly low overcurrent protection setting. And so hopefully won't need to worry about that. So yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave comments, questions, suggestions down in the comment section below. Oh, and I forgot to mention that if you do want to get this data sheet yourself to like read through it more, you can find it, like you can literally just Google it. Like that's where I get all of my data sheets. Well, no, I don't actually get all of them from Google, but just normally I just go to like the manufacturer website and look up the part number. So that's kind of that. Anyway, so yeah, like, share, subscribe, leave a comments, questions, suggestions down in the comments section below, or any corrections. I may have made some mistakes here just because, well, I made mistakes in the last time I tried to do like when I did this same kind of video for the UP9511, I actually had a mistake with the, I got the way the current limiting system on that, well, the overcurrent protection on that chip worked. I got it backwards. So I said you should like, I can't remember what I said, but I got it backwards. Like I said it was like to lower the overcurrent protection, was to raise the overcurrent trip point. You should do something. And it was like, I said the exact reverse of what it actually was. But the thing is just like, if you set the OCP too low, it's just going to shut down. So then you'll know that you've set it too low. So you can just raise it up again afterwards. So it's not like it's not, in my opinion, as far as I'm concerned, that's not like a massive critical error to make, right? Like if your goal is to not have overcurrent protection, accidentally setting it too low is not really a problem. It's not like it's not like screwing up the voltage control, where if you put the voltage control, like if you set your voltage control up wrong and have 2 volts going straight to ref in, yeah, you're going to have a dead card. So anyway, as that, and also if you'd like to support actually hardcore overclocking, I have a Patreon and there's t-shirts you can buy. You can find a link to all of that down in the description below. And yeah, that's it for this video. Yeah, if you want to modify any card using an NCP81274, there's actually quite a lot of them from NVIDIA. Like this is a pretty popular controller for NVIDIA GPUs. Well, if you have a card using one of these, then well, now you at least know where the datasheet is. If you didn't find my attempts at explaining how to mod this thing particularly helpful. So yeah, that's it, and goodbye.